Hi, everyone. I hope you're doing well. We've been talking about quantum mechanics, and today we're going to look at one of the most fascinating and well-known quantum phenomena. That's the phenomena of tunneling. In tunneling, we find that a particle has some probability of passing through a barrier, even if classically there's no possibility that that could occur. Okay? Well, really exciting. Here, let's take a look at an outline and see where we are. Very good. So we've been talking about quantum mechanics. Most recently, we used the time-independent Schrodinger equation to talk about a number of different scenarios. We looked at free particles, and we investigated, well, of course, free particles in the case where the potential energy is constant everywhere in space, but also the interesting problem of the step potential. And here we looked at two cases, the case where the energy of the particle is greater than the height of a barrier, and we can see reflection and transmission at the barrier, and also the case where the energy of the particle is less than the height of the step barrier, in which case we saw barrier penetration. After that, we discussed bound particles, and we looked at a few simple potentials in which electrons or particles can be bound, giving quantized energy states. And these included the infinite well, which is notable because it's such a simple problem, and yet it gives us all of the things we expect for a quantum bound particle system: quantized energy states, well-described wave functions for the different orbitals, so to speak. We also looked at the finite well, which was a more complicated problem, that's still very interesting. It had some resemblance even to the step potential problem. And finally, most recently, we talked about the quantum harmonic oscillator. Which, along with the hydrogen atom, are the most important systems that we'll talk about in this course. Okay? Well, today we're going to go back and talk about one more free particle situation, and that's the situation of tunneling. And we're going to talk about a particle incident on a square barrier. Okay? Here, let's see how the problem looks. So to talk about tunneling, it's important or useful just to review what we found for the step potential. And in particular for the case where the height of the step is greater than the energy of the particle. In this case, which I'm just going to sketch for us here, if this is the height of the barrier, and if the energy of the particle is below the height of the barrier, then what we found is that the wave function is oscillatory to the left of the barrier. But when we reach the barrier, because the energy is less than the height of the barrier, U minus E naught E minus U naught becomes a negative quantity, and as a result, the wave function becomes a decaying exponential. Let me try and draw that again here. Okay, but importantly, the wave function can still leak into the barrier, in a phenomenon we call barrier penetration. Okay? Square, or actually, let me call this the rectangular barrier. Okay, so that result that we just saw raises a really interesting idea. It raises the idea that if we had a potential that looked like this, which steps up for a short distance and then steps back down, that if we had a particle incident on this barrier, even if the energy of the particle was less than the height of the barrier, we might get transmission through the barrier. And here's why. To the left of the barrier, the incident particles and reflected particles are described by an oscillatory wave function. Within the barrier, we expect that the wave function will decay exponentially. But if the barrier has a finite thickness, it's not too thick, we just draw that again, the wave function will still be finite when we reach the right side of the barrier. There we are. And so at that point, we expect that there's a finite probability the particle will be transmitted here. And then we'll have an oscillatory wave function to the right. And because the wave function amplitude isn't zero on the right, that means the probability of transmission is greater than zero. The particle has some probability of passing through the barrier. Of course, this is remarkable because classically that can't occur. The classical analog of this situation is something like this. We imagine a particle that gains kinetic energy by, say, rolling down a hill, and then it comes to a barrier. If the particle starts at a height which is below the top of the hill, then there's no way that the particle can possibly transmit over the barrier. Here's our particle, or our ball, starting at this point. It rolls down the hill and gains kinetic energy. And then it rolls up the hill at the barrier. But when it gets to the point where the energy is equal to the potential, energy is equal to the potential energy, the kinetic energy goes to zero. And so the particle turns around and comes back. There's a turning point here. And there's no situation where the particle can ever get over the barrier. So the transmission probability classically would be zero. Okay? So that's what's remarkable about this problem. So we'd like to take a closer look at this rectangular barrier problem and see if it's really true. And also see if we can get an expression for the transmission probability. And that's what we're going to do in the next few videos. You'll actually look at some videos I made a few years ago. I thought I did a nice job on those, so I don't see a reason to re-record them. So that should be fine. So, well, here, let's stop this video and then we'll get started with that.